Thank you, Dr. Niederman. I would like to thank the selection committee for highlighting this research area by this prestigious award. So I work on the area, it's really at the interface between material physics and thermal engineering. So I think like my students and my colleagues in the field are excited like this award is being given to this area. So I'm going to divide my talk into 3 different application areas. They are all related, share a similar fundamental principle. The first one is on thermoelectric energy conversion. The second one is on thermal management of electronics. The last one is on thermal energy storage. About like 90% or even more of that of the energy we use involves some sort of thermal energy transport, conversion, or storage processes. In the industrial sector, anywhere between 20 to 50% of the energy input is lost eventually as waste heat. Okay. In the transportation sector, more than 50% of the vehicle fuel energy is lost as either the exhaust gas, very hot exhaust gas as waste heat. The temperature is actually quite high. It's as high as about 600 C. We consider this as a high quality heat actually. So the major automakers, several major automakers, they have been looking into technologies to recover this waste heat and convert it into electricity. Okay, so you can increase your fuel efficiency of the vehicles. Okay, one of the leading candidates is based on this solid-state thermoelectric devices. Okay, this is based on so-called sit-back effect. Okay, it's made of a semiconductor p-n junction. Okay, so when you place this p-n junction between a heat source and a heat sink, the majority charge carriers in the entire semiconductor is electrons. The majority carriers in the p-type semiconductor is holes, is positive charges. Both of them will diffuse from the heat source to the heat sink, so will generate a electrical power output. Okay, so basically the power output is related to the sit-back coefficient, which is defined as the thermal voltage, the voltage generated by the temperature difference, thermal voltage output per unit temperature difference. It's a reliable technology. Okay, it does not have any moving parts. Okay, it will not fail as easily as your combustion engine. Okay, but then the issue is that the efficiency is not very high as of now. It's only 2 to 5%. Okay, and it's very costly. It's like $20 to $30 per watt. This kind of cost range, and the high cost is related to the materials used. Okay, most of the thermoelectric materials contains of bismuth telluride, lead telluride, and silicon germanium. Okay, and this, if you look at the this materials availability chart, okay, so tellurium is one of the rarest materials, okay, elements, okay. Germanium is also very expensive, okay. That's one of the reasons this technology is very expensive. So there's a lot of interest of using this particular materials, basically is earth-abundant materials, to develop a high-efficiency thermoelectric materials. Okay, so that's one of our focus, our research. So the efficiency is limited, again, related to the material's properties. This magic number of figure of Mary, we call it ZT, okay? It depends on 3 properties. The sit-back coefficient I introduced previously, okay? If you have high sit-back coefficient, you can generate more thermal power. We need to have high electrical conductivity to reduce the loss by like electrical heating, Joule heating. We actually need low thermal conductivity so that the heat will not loss from the heat source to the heat sink directly. Okay, you can use the heat to actually convert into electricity. Okay, a ZT number larger than 2 or 3 will enable widespread use of thermoelectric devices, not only for thermoelectric waste heat recovery, also for example, household refrigerations, okay? So, but the existing materials has limited ZT number, okay? Like over half of a century, okay? The peak ZT number at different temperatures, okay? It's like basically states near a value of unity, okay? In the last decade, okay, there's some great progress in this area, okay, using manipulating the electronic band structure by doping, okay, to increase this S squared sigma, we call it power factor, or by using either nanostructures or complex structures to reduce the thermal conductivity. Okay, these two approaches have increased the ZT value to be somewhere close to about 1.5, close to 2 now. Okay, so it's really an exciting area to work on thermoelectrics. Okay, actually, the earlier work on semiconductors actually is not for making field effect transistor devices. At that time, no one knows those concepts. Actually, it's mostly for making thermoelectric converters. Okay, now I think it's a really good time to come back to look at this concept. Okay, so for example, if you look at this work, okay, just by making nanostructural bismuth antimony telluride, the ZT can be increased by 40%. Actually, the author of this work is in the audience, Professor Ren, when he was in Boston. So, so it looks like by engineering the thermal conductivity of materials is really a promising approach to enhance this thermoelectric conversion efficiency. Okay, so but we need to understand like how really to do this. Okay, the thermal conductivity has two contributions. One is from electrons. Electron can also carry heat. The other is from phonons, which is quantums of lattice vibration. This is lattice waves. Okay. The electronic contribution to thermal conductivity is proportional to electrical conductivity by the Wiedemann-Franz law. So you cannot really lower the electronic contribution, okay, without hurting the electrical conductivity. So we have to focus on the phonon contribution. The phonon contribution has contribution from phonons from different polarizations and different wavelengths. It's proportional to the heat capacity of phonons, their velocity, and their scattering mean-free paths or scattering lanes. Okay, we can like somehow manipulate the scattering to manipulate the thermal conductivity. There are different scattering processes. Phonons can scatter with phonons, and phonons can be scattered by point defects. Okay, but atomic point defects, they are not effective scatterers for long wavelength phonons. This is just like the sunlight, the long wavelength sunlight are not scattered by the molecules in the atmosphere. It's the same principle, okay? But then using like embedded nanostructures with larger size or using grain boundaries, you can scatter those like long wavelength phonons that carry a lot of heat in crystals. So today I'm going to talk about our work on this materials. It's manganese silicide, okay? It contains both elements in this materials are earth abundant, okay? And it's a crystal, but it has a thermal conductivity lower than even alloy, as close to the thermal conductivity of the state of our thermoelectric materials, which is bismuth telluride, okay? And the low thermal conductivity of this material is related to its very complex structures. Okay, it has two like sub-lattice. One is the manganese, one is silicon. Okay, so they are lattice constant along the C-axis. Okay, these two lattice constants, they are not perfectly proportional to each other. So when you put them together into a HMS, this higher manganese silicide lattice, okay, the unit cell along the C-axis could be as long as tens of nanometers. Nanometer is small, right, in our eyes, but actually in that scale, it's a big compared to the lattice constant along the B-axis, okay? And we have measured the phonon energy versus wave number dispersion of this manganese silicide crystal using neutron scattering. what we find, this is work done in the Oak Ridge. What we find is very interesting. Okay, along the BSs, this is basically you look at these short lines. Is actually the phonon branches. Okay, if you look at the CSs, the phonon branch is very broad compared to the phonon branches along the BSs. Okay, this actually is related to the very complex structure, large lattice constant along the CSs. Okay, and this like a broad phonon branches actually provides more phase space or provide more channels for phonon and phonon to scatter with each other. As a consequence, the thermoconductivity of this single crystal is as low as like almost amorphous materials. We have done further work with collaborators who can make nanostructures of these materials. They can grow nanowires of this silicide. And we have established methods that can actually measure the all the thermoelectric properties of one single nanowire. What we find, this measurement places the thermoconductivity of this complex silicide nanowire to be as low as the thermoconductivity of glass, amorphous glass. So this is a single crystal, but you can get the thermoconductivity as low as glass and with still high electrical conductivity. This is very promising. But then you cannot really use a single wire to make useful thermoelectric devices. You have to make energies or deal with large-scale applications. You have to make large-scale materials. So then we further our research by developing ball nanostructural complex silicides. Okay, we again use the complex crystal structure to scatter high-frequency phonons. And then we use this interface of the nanostructures to scatter long wavelengths, low frequency phonons to obtain amorphous glass-like thermoconductivity. Okay, so our goal is really achieve a state-of-the-art ZT value, but in this Earth-abundant materials, so lower the cost of thermoelectric energy conversion technology. I'm going to move on to talk about the second area related to thermal management of electronics. So in the US, the IT infrastructure, including data center, use more than 20 gigawatt of energy. Okay, this is about 5 to 10% of US electricity budget. Okay, and this energy is eventually is dissipated as heat. Okay. And if you look at the transistor devices, now we have many large number of transistors per CPU, okay? But then the energy dissipation by the CPU, per unit area, we call it power density, okay? Also increase almost exponentially, actually faster than exponential, okay? And currently, the power density of a state-of-the-art CPU is comparable to the power density of a nuclear reactor. So it sounds quite scary, right? So, and this is actually not the end of the picture yet. Okay, the power density value I gave you is the average on one CPU. Okay, but if you look at the device area, okay, it could be even higher, order of magnitude higher. Okay, and locally the temperature could be very high. This is an example. This is problem not only for commercial silicon devices. It's also the problem for other new device structure based on, for example, here I show a graphene field effect transistor. Okay, we again have another technique. We call it scanning thermal microscopy. We can measure the temperature distribution of devices with a spatial resolution of tens of nanometers. We use that. We find out really there's a hotspot near the drain region, okay? And even the average temperature along the channels could be hundreds of degrees higher than ambient, okay? So this is actually a big reliability concern, okay? At this temperature, a lot of things can happen, okay? So, and this heating issues related to the thermal properties. For example, the graphene field effect transistor, the graphene is basically the parent materials of graphene is graphite. Graphite is basically stacking graphene together. Graphene is one single layer of carbon atoms, okay? So, and this is actually a high thermal conductivity materials. In principle, it should help to dissipate the heat from the hot spot to the cold region, right? So why we see such a hard devices. Okay, not only graphene, another structure, boron nitride. Okay, it can also come with hexagonal boron nitride. This is one of the structures. Okay, and similar to graphite, it's a high thermal conductivity dielectric. Okay, and there are a lot of interest to use like a thin hexagonal boron nitride and single layer graphene to make different kind of electronic devices. And both UT Austin and Rice University are leaders in this research area. So, but this is a question, okay? When we reduce the thickness, layer thickness, okay, can you assume the thermal conductivity, the thermal property, would that be the same as graphite or HBM? Okay, that's the question we want to answer. Okay, and first of all, we need to look at, again, the phonon dispersion, the frequency versus wave number dispersion, okay? So in graphene, you only have one single layer of carbon atom. You don't have, this carbon atoms do not interact with adjacent carbon layers. Because of that, okay, you have a fewer phonon branches, fewer phonon modes, okay? In graphite, first of all, you have phonons propagating perpendicular to the basal plane. You have this is the gamma A direction. You have a lot of modes here. Even for the basal plane, okay, this you have additional optical modes, okay, and this additional modes again providing additional channels phonon to scatter with phonons and reduces thermal conductivity. So because of that, there are a number of theoretical calculations show that, okay, as you reduce the layer thickness of graphite, okay, to single layer graphene, the thermal conductivity can be even higher, okay? So, and there's also experiment showing that, okay, for suspended a few layer graphene, as you reduce the thickness, the thermal conductivity can be increased to be above the value for graphite, okay? But then when you make devices, the graphene is not suspended. It's supported on a substrate or embedded in a medium, okay? It can behave differently, okay? And we actually show that this is really the case. We developed another method to basically study a thermal transport of graphene supported on silicon dioxide, okay? What we find is the opposite trend, okay? As the thickness increase, or as the thickness decrease, the thermal conductivity of this supported multi-layer graphene actually decrease and fall below the value of graphite, okay? And similar trend has also been found by another group on embedded graphene, okay? So this is really due to the interaction between graphene and the amorphous substrate, okay? The amorphous substrate actually scatter the phonons inside the supported or embedded graphene, okay? And this effect is observable even in thick multi-layer graphene as thick as 30 layers, even more, okay? Not only amorphous support can suppress the thermal conductivity of graphene, okay? If there is contamination on the graphene surface, for example, we have this polymer coating on the graphene surface, the thermal conductivity is also lower than the thermal conductivity of graphite. And this is also true for hexagonal boron nitride, okay? So again, this is interesting materials. It's a dielectric, and graphene is a semi-metal, okay? Dielectric has its own application in electronic devices. And when you place graphene on hexagonal boron nitride support, you can get higher electron mobility than graphene on amorphous oxide, okay? What we find is that when we increase the layer thickness of this supported few layer HBN from about 5 layer to about 11 layer, we can recover the bulk thermal conductivity of hexagonal boron nitride, okay? This provides a design guideline for how to design this few layer HBM as a support layer for graphene or for silicon devices. So, yeah, the thermal conductivity of graphene coated by polymer is lower than graphite, okay? But the value is still quite high. It's still higher than the thermal conductivity of copper, okay? So, and it has high surface to volume ratio. So this makes it desirable for applications such as the fillers. You can fill these materials in polymer to increase the thermal conductivity of polymers to obtain high thermal conductivity, high strength polymer, okay? So, and for example, this work shows that graphene fillers actually perform better than nanowires or nanotube fillers, okay, in terms of thermoconductivity enhancement. But then this thermoconductivity value is still low, okay? It's not reaching the limit, okay? So that can be achieved, okay? Because the problem is there's interface thermal resistance between these graphene plates, okay? To solve that, okay, we investigate this like a continuous covalently bonded like graphite, ultra-thin graphite phone structure or graphene phone structure. When we achieve like all the magnitude of higher thermal conductivity than those van der Waals bonded like carbonyl structure network, okay? And we apply this, one application of this high thermal conductivity phone like structure is used as the high thermal conductivity substrate for flexible electronic devices. Our new like NSF Engineering Research Center is focused on basically making mobile computing devices. And this device is made on this flexible plastic substrate, which has very low thermal conductivity. So basically, this is one approach we are taking now to increase the thermal conductivity of the substrate. So actually, we have results showing that when you make graphene devices on plastic substrates, the substrate will melt, okay? It will not work, okay? So this is some ongoing work we are working on. My time is almost up. I just touched briefly on the last application area of thermal energy storage. Basically, Department of Energy identified a number of needs for technologies, new technologies for high energy densities, for thermal storage with high energy density, okay? So this needs can be for like building heating. For example, you can store solar heat in the day and use it at night, okay? And this thermal storage unit can be also used to provide heating and cooling to electrical vehicles, okay, without using the electrical energy from electrical battery, okay? There are also other applications at higher temperature, okay? So phase change materials is one like leading approach for thermal storage, okay? So the different phase change materials with different energy density at different melting temperature, okay? A common issue is that the energy density of this phase change materials, of this thermal energy storage energy density, is low compared to the energy density in electrical battery, okay? And also the thermal conductivity of this material is also very low. It limits its power capacity, okay? So it would be great if someone can invent materials with like energy density like above 700 megajoule per meter cube. That's comparable to electrical battery, and a temperature range, for example, relevant to heating and cooling applications. So we have a joint program with Chris Belowski in our chemistry department, and also Rod Ruoff in our materials department, okay, to basically, first of all, we use this ultra-thin graphite foam, which we have worked on for a few months now, okay, to enhance the thermal conductivity of phase change materials. We also look at ways to engineer the molecular structures of sugar derivatives. These are phase change materials. So, so it would be cool, like in the future, like your electrical vehicle is actually powered up by sugars. So, all right. Just as a summary, our fundamental research pointed out that by combining the complex structure approach and the nanostructuring approach, we can achieve glass-like thermal conductivity in crystal structures. Okay. We also show that when like graphene and HBN are in contact with an amorphous solid, the thermal conductivity will be reduced. But then even the reduced thermal conductivity is still quite high. And by solving the interface problems using this foam structure, we may have a good answers or good approach to solve the thermal management problems for both electronics and energy storage technologies. Again, this was done with a large number of students and colleagues, both inside UT and outside UT, and supported by several federal agencies. Thank you for your attention.
I have a question. At the beginning, you mentioned some semiconductors are very expensive, so you're trying to use like graphene, sorry, and a carbon nanotube to replace that. But also, this graphene and carbon nanotube is still very expensive today. So how could you lower the cost?
Actually, the first price on thermoelectric materials, the new materials we're looking at is manganese silicide. Okay, both manganese and silicons are earth-abundant materials. Actually, the technique we are using is all like a ball synthesis. We grow a very large quantity of materials. Those are much cheaper than like the conventional like bismuth and other materials. But graphene and graphene, if you look at it, graphene is from graphite, right? Graphite is actually earth-abundant materials. It's very dirt cheap. So if one can invent methods to grow large area graphene using graphite source, okay, I think it's going to be a low-cost approach. So.